There is a question so large that most people never dare to ask it all the way to the end. Not just where did everything come from, not just how will everything end, but both, simultaneously, held together like two edges of a blade, the complete arc of existence, from the first trembling instant of reality to the last dying ember of a universe grown cold beyond imagination. Most stories begin somewhere in the middle. This one begins before the beginning and ends after the end. And somewhere in between, there is a small, warm planet, spinning quietly around an ordinary star, in an ordinary galaxy, in a cosmos so vast that the numbers used to describe it have no meaning in ordinary human language. And on that planet, creatures made of ancient stardust looked up and began to wonder. That act of wondering, fragile, improbable, brief, is itself one of the most extraordinary things the universe has ever produced. But before we get there, we have to go somewhere far stranger. We have to go to the moment before light existed, before space existed, before time existed. We have to go to the very edge of what the laws of physics can describe, and then peer over that edge into the dark, because that is where the story begins. Imagine removing everything, not just the stars, not just the galaxies, not just the planets and the gas and the dust and the radiation. Imagine removing space itself. Imagine removing time. Imagine a condition so alien that the word nothing does not even accurately describe it. Because nothing is still a word we use inside time, and there was no time. There was no before. There was no darkness waiting. There was no silence. Because silence requires space to move through, and space did not exist. And then something happened. Physicists call it the Big Bang, which is an almost comically inadequate name for what it actually was. It was not an explosion in space. It was the creation of space. It was not an event that happened somewhere. It was the event that created somewhere. It was not a moment in time. It was the moment that created time. Everything you have ever touched, everyone you have ever loved, every mountain, every ocean, every star you have ever seen on a clear night, every atom in your body, all of it emerged from a single point of infinite density and infinite temperature, in a fraction of a second so small that it makes 1 second look like an eternity. And here is the first mystery. We do not know why it happened. We do not know what caused it. We do not know whether it was the first time. We do not know whether there were other universes before it or beside it, or whether the concept of before even has meaning when applied to the birth of time itself. What we do know is that it happened, and what followed was the most violent, most creative, most improbable sequence of events in the history of anything. This is the story of all of it. The universe, at the very first instant, was not the universe we know. It was something almost incomprehensible, a state of matter and energy so extreme, so compressed, so ferociously hot, that the fundamental forces of nature did not yet exist as separate things. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, the 4 pillars upon which all of physical reality is built, were unified. They were one. A single, seamless, superforce flowing through a space smaller than any particle we have ever detected. The temperature was 10 to the 32nd power degrees, a number so large that if you wrote it out, the zeros would fill a library. Physics has a name for this first moment, the Planck epoch, named after the physicist Max Planck, who first began to quantify the smallest meaningful scales of reality, and the Planck epoch lasted for Planck time, approximately 10 to the negative 43rd seconds after the Big Bang, which is so brief that it makes every other unit of time in human experience look infinite by comparison. During the Planck epoch, our current understanding of physics breaks down completely. The mathematics we use to describe gravity, Einstein's general relativity, and the mathematics we use to describe the subatomic world, quantum mechanics, cannot both be true simultaneously at these extremes. They contradict each other. They produce infinities where there should be numbers. They give nonsense answers to meaningful questions. This is not a small problem. It is perhaps the deepest unsolved problem in all of science. We do not have a complete theory of quantum gravity. We do not have a single coherent framework that describes reality at the Planck scale. And so the very first instant of the universe remains, to this day, a mystery sealed behind the limits of our mathematics. What we can say is this: the universe existed. And then, in a way we do not fully understand, it began to change. At 10 to the negative 36th seconds after the Big Bang, still an almost inconceivably brief moment, something happened that would shape everything that followed. The superforce began to separate. Gravity split away from the other forces. The universe cooled, fractionally, and in that cooling, the symmetry shattered. And then the universe inflated. Not expanded, inflated. Those words mean very different things. Expansion is the gradual growth of space. Inflation was something else entirely. An exponential, explosive, almost instantaneous stretching of the fabric of space itself, driven by a mysterious energy that physicists call the inflaton field. During inflation, which lasted from approximately 10 to the negative 36th to 10 to the negative 32 seconds after the Big Bang, the universe grew from something smaller than a proton to something roughly the size of a grapefruit. That sounds small, but consider the scale of the expansion. The universe grew by a factor of at least 10 to the 26th. Some estimates suggest it grew by a factor of 10 to the 50. In a time period so brief that the word brief does not begin to capture it. If you took a single atom and inflated it at the rate the universe inflated, it would become larger than the observable universe in a fraction of a second. The stretching of space during inflation was faster than light, which does not violate Einstein's relativity because nothing was moving through space. Space itself was moving. Inflation solved several deep puzzles that had haunted cosmologists. It explained why the universe, in all directions we look, appears to have nearly the same temperature, because everything we observe was once in causal contact, squeezed together before inflation stretched it apart. It explained why space appears to be geometrically flat rather than curved. It explained why we do not observe certain exotic particles that should have been produced in great quantities in the early universe. Inflation diluted them to near zero density. But inflation introduced a mystery of its own. What caused it? What is the inflaton field? Why did inflation stop when it did? And here is the stranger question. Did it stop everywhere? Some cosmologists believe that inflation, once started, never truly stops. It stops in some regions, like ours, which settle into stable universes. But elsewhere, in regions beyond our cosmic horizon, inflation continues eternally. spawning new universes in a process called eternal inflation. In this picture, our Big Bang was not the beginning of everything. It was the beginning of us, one bubble of stable physics in an infinite churning sea of eternal inflation. This is the multiverse hypothesis, and it is one of the most controversial and fascinating ideas in modern cosmology. It makes predictions that may be fundamentally untestable, which troubles many physicists, and yet it emerges naturally from inflation, which itself is supported by compelling observational evidence. So we are already, at the very first second of the universe, standing at the edge of something we cannot fully see. And the story is just beginning. When inflation ended, the energy of the inflaton field did not simply vanish. It transformed, a process physicists call reheating. The inflaton decayed into a ferocious plasma of particles and antiparticles. The universe, now vastly larger than it was a fraction of a second ago, was still inconceivably hot and dense. And in that plasma, the fundamental particles of matter were being created and destroyed in a furious, rapid equilibrium. Quarks, gluons, electrons, neutrinos, photons, and their antimatter counterparts, antiquarks, positrons, antineutrinos. This is where something happened that we still do not fully understand. Something that, had it gone differently by even the smallest margin, you would not be here. Nothing would be here. The universe would have flashed into existence and immediately annihilated itself into pure energy. The problem is symmetry. The laws of physics, as we understand them, treat matter and antimatter nearly identically. When matter is created, antimatter is created in equal amounts. When they meet, they annihilate each other in a burst of pure energy. In the first fraction of a second, the universe was producing matter and antimatter in roughly equal quantities, and they were annihilating each other as fast as they were created. If the universe had been perfectly symmetric, if matter and antimatter had been produced in exactly equal numbers, they would have destroyed each other completely, leaving nothing but radiation, a universe of pure light, with no matter at all, no stars, no planets, no atoms, no you. But something was not symmetric. For reasons we do not yet fully understand, the universe produced slightly more matter than antimatter. Roughly one extra matter particle for every billion matter-antimatter pairs. When the annihilation was complete, that tiny surplus survived. And that surplus, that almost impossibly small asymmetry, is everything. Every star, every galaxy, every atom of every living thing that has ever existed is descended from that surplus. Physicists call this asymmetry baryogenesis, and they know it must have happened, but they do not know exactly how. The standard model of particle physics predicts some asymmetry between matter and antimatter, a property called CP violation, but not nearly enough to explain the ratio we observe. There must be additional mechanisms, additional physics beyond the standard model that we have not yet discovered. The very existence of matter, of everything, is an unsolved problem. At 1 microsecond after the Big Bang, the universe had cooled enough for a new kind of transition to occur. Quarks, which had been free-floating in the plasma, began to bind together into larger particles, protons and neutrons. This is the transition from the quark-gluon plasma to the hadronic era. The strong nuclear force, which had been too weak at higher temperatures to hold quarks together, now became dominant. protons and neutrons formed in enormous numbers, and then immediately began to collide and annihilate with antiprotons and antineutrons. The universe was a furnace of creation and destruction, so violent and so rapid that no individual particle existed for long. But the asymmetry that favored matter persisted, and when the annihilation was finally complete, the surviving protons and neutrons, the products of that 1 in a billion imbalance, were all that remained. 1 second after the Big Bang, the universe was roughly 10 billion degrees. Neutrinos, which barely interact with anything, had already decoupled from the rest of the matter and energy and were streaming freely in all directions. They still are, even now, a cosmic neutrino background, permeating all of space, carrying information about the very first second of the universe. We have never directly detected it, but we know it is there. The universe was now a plasma of protons, neutrons, electrons, and photons. The photons were trapped, scattering continuously off the charged particles, unable to travel more than a tiny distance before bouncing off something. The universe was opaque, a thick, glowing fog of radiation and matter, so bright that if you could somehow stand inside it, you would be instantly vaporized by the intensity of the light. Between 1 second and 3 minutes after the Big Bang, a process began that would determine the basic chemical composition of the entire universe. Physicists call it Big Bang nucleosynthesis. Protons and neutrons began to fuse. The temperature was still high enough, around 1 billion degrees, to force them together, despite their natural repulsion. A proton and a neutron combined to form deuterium, a heavy form of hydrogen. Deuterium fused with more protons and neutrons to form helium-3 and helium-4. Trace amounts of lithium and beryllium were also produced. And then it stopped. After roughly 20 minutes, the universe had cooled enough that nuclear fusion could no longer occur. The plasma that had existed was now mostly fixed in its composition, roughly 75% hydrogen by mass, 25% helium, and tiny traces of heavier elements. This prediction, made from first principles using nothing but the laws of physics and the measured expansion rate of the universe, matches perfectly with what we observe in the oldest stars, in intergalactic gas, in the cosmic microwave background radiation. It is one of the great triumphs of cosmology. But it created a new mystery. 75% hydrogen, 25% helium, and almost nothing else. Where did carbon come from? Where did oxygen, nitrogen, iron, calcium? Where did the elements of life come from? They did not exist in the early universe. They were not produced in the Big Bang. The early universe was chemically simple in a way that makes it almost impossible to imagine how we got here. The complexity of life, of chemistry itself, beyond the most basic level, required something that did not yet exist. It required stars. The universe, at 380,000 years after the Big Bang, underwent one of its most dramatic transformations. The plasma had been cooling steadily, and now it reached a critical threshold, a temperature of about 3,000 degrees. At this temperature, electrons slowed enough to be captured by protons and atomic nuclei. For the first time, neutral atoms formed, hydrogen atoms, helium atoms. The electrons that had been scattering photons in every direction were suddenly gone, bound into atoms that interacted with light far less aggressively. For the first time, the the universe became transparent. The photons that had been trapped in the plasma for 380,000 years were suddenly free. They streamed outward in every direction, carrying with them a perfect snapshot of the universe at that moment, its temperature, its density, its tiny fluctuations. Those photons are still traveling. We can detect them today. We call them the cosmic microwave background radiation, and they are the oldest light in the observable universe. Mapped in extraordinary detail by satellites including COBE, WMAP, and Planck, the CMB shows us a portrait of the universe at 380,000 years of age. Nearly uniform in temperature, differing by only 1 part in 100,000 from one direction to another. Those tiny fluctuations in the CMB are among the most important objects in cosmology. They represent the seeds, the initial density variations from which everything else grew. Regions that were very slightly denser than average had slightly stronger gravity. Over millions and billions of years, that slightly stronger gravity would pull in more matter, which would increase the gravity further, pulling in still more matter. The universe was beginning, in the slowest and most majestic way imaginable, to structure itself. But first, it had to pass through the dark. After the CMB photons were released, the universe entered a period that cosmologists call, with elegant simplicity, the cosmic dark ages. The photons had departed. No new sources of light yet existed. The universe was filled with neutral hydrogen and helium gas, dark, silent, slowly cooling, slowly drifting. From approximately 380,000 years to perhaps 150 million years after the Big Bang, the universe was dark. Not the darkness of a room with the lights off, not even the darkness of a moonless night far from any city. A darkness so total, so absolute, that there was not a single photon of visible light anywhere. The universe existed in a state of perfect, impenetrable obscurity. And within that darkness, gravity was working. The tiny density fluctuations in the gas were slowly amplifying. Regions of slightly higher density were attracting more matter, growing denser. Matter was flowing along invisible threads, gathering at intersections, piling up in great filaments and sheets and nodes, a cosmic web whose basic structure was being laid down in silence and darkness. And then, one by one, the first stars ignited. The first star, wherever it was, whenever it formed, is one of the most significant events in the history of the universe. It ended the cosmic dark ages. It introduced, for the first time since the CMB radiation departed, a source of visible light into the universe. And it began the process that would eventually create every complex element in the periodic table. These first stars were extraordinary objects. Astronomers call them population 3 stars, and they were unlike anything that exists in the universe today. They formed from pure, pristine hydrogen and helium, untainted by any heavier elements, because no heavier elements yet existed. And because they lacked the metals that modern stars use to lose energy during collapse, they had to grow much larger before the pressure at their cores was sufficient to ignite nuclear fusion. Population 3 stars were likely massive beyond anything in the modern universe, perhaps hundreds of times the mass of our Sun. Some may have been thousands of solar masses. Their lives were correspondingly brief. A star's lifespan is inversely related to its mass. The more massive a star, the faster it burns through its fuel. These titans, fueled by vast stores of hydrogen, but burning at temperatures and pressures inconceivable to us, likely lived for only a few million years. Brief even by stellar standards. But what they did in those few million years was extraordinary. Inside the cores of these first stars, nuclear fusion was fusing hydrogen into helium, and then helium into carbon, and then carbon into oxygen, neon, silicon. Each fusion reaction creating new elements, building the periodic table step by step, layer by layer. When the core of a massive star finally runs out of fuel, it collapses in a catastrophic instant, triggering a supernova explosion of almost incomprehensible violence. In those explosions, the intense energy and neutron flux drove further fusion reactions, creating elements heavier than iron, gold, silver, platinum, uranium, that cannot be produced by normal stellar fusion alone. And those explosions scattered the newly created elements into space. The gas clouds of the early universe, previously pure hydrogen and helium, were now seeded with carbon, oxygen, nitrogen, iron. The raw materials of chemistry, the raw materials of life, with every generation of stars that was born, lived, and died, the universe grew chemically richer. The second generation of stars, population 2 stars, formed from gas already enriched by the explosions of population 3 stars. They were smaller, longer-lived, more like stars we see today. And when they too eventually died, they enriched the gas further still. The universe was building complexity. Slowly, over hundreds of millions of years, it was accumulating the ingredients necessary for everything that would follow. And during all of this, something else was happening. Something that would prove to be one of the deepest mysteries in modern science. The universe was being shaped by something that could not be seen. Astronomers studying the rotation of galaxies in the 1970s noticed something that did not add up. The outer edges of galaxies were rotating at nearly the same speed as the inner regions. This should not have been possible. By Newtonian gravity, the outer regions of a galaxy, farther from the concentrated mass at the center, should rotate more slowly, just as the outer planets of our solar system orbit more slowly than the inner ones. But they did not. The rotation curves were flat. The outer stars were moving far too fast to be explained by the visible matter alone. The conclusion seemed inescapable, though it was deeply uncomfortable. There must be additional matter. Matter that does not emit light, does not absorb light, does not interact electromagnetically at all. Matter that is detectable only through its gravitational influence. Matter that is invisible. Astronomers call it dark matter. And the evidence for its existence is now overwhelming. We see its gravitational effects in the way galaxy clusters bend the light of objects behind them. Gravitational lensing. We see it in the large-scale structure of the universe. The cosmic web could not have its observed shape without dark matter providing the gravitational scaffolding. We see its signature in the cosmic microwave background. Dark matter does not consist of ordinary atoms. It is not made of protons and neutrons. It is something else, some kind of particle, or perhaps particles, that interacts with gravity, but barely at all with anything else. The leading candidate for many years has been a class of particles called weakly interacting massive particles, or WIMPs. But despite decades of increasingly sensitive experiments, detectors buried miles underground to block cosmic rays, detectors sent to space. WIMPs have not been found. Dark matter constitutes approximately 27% of the total energy content of the universe. Ordinary matter, everything we can see, everything we have ever built a physics experiment to study, constitutes only about 5%. 5%. The universe we know, the universe of atoms and light and chemistry and biology and civilization, is a thin film of ordinary matter floating in a vast sea of things we do not understand. And there is more. In 1998, two independent teams of astronomers were studying supernovae in distant galaxies. Their goal was simple: to measure the rate at which the universe's expansion was slowing down. Because, of course, it was slowing down. The gravitational attraction of all the matter in the universe should have been decelerating the expansion that began at the Big Bang. They measured it, and what they found was one of the most shocking results in the history of science. The expansion was not slowing down, it was speeding up. The universe was not decelerating under the pull of gravity. It was accelerating. Something was pushing galaxies apart, overcoming gravity on the largest scales, causing the expansion of space to accelerate with time. That something, unknown, unnamed, described only by its effects, was called dark energy. And dark energy constitutes approximately 68% of the total energy content of the universe. Think about that for a moment. 68% dark energy, 27% dark matter, 5% ordinary matter. Everything we know, every particle in the Standard Model, every atom in every galaxy we have ever observed, every photon of light that has ever crossed space, constitutes 5% of the universe. The remaining 95% is something else entirely. Einstein had actually predicted something like dark energy. In his original field equations for general relativity, he introduced a term called the cosmological constant, a property of space itself that would resist the gravitational collapse of the universe. He later called it his greatest mistake, when Edwin Hubble's observations showed that the universe was expanding, not static as Einstein had believed. But the cosmological constant, it turns out, may have been right all along. Not to prevent collapse, but to drive acceleration. Dark energy may be the energy of empty space itself, a quantum property of the vacuum, an intrinsic property of space-time that pushes outward with a constant density regardless of how much space exists. As the universe expands and more space is created, more dark energy is created along with it, driving the expansion to accelerate faster and faster. If this is true, and we do not know that it is, because we do not truly understand what dark energy is at a fundamental level, it has enormous implications for the ultimate fate of the universe. Implications that are deeply strange and more than a little unsettling. But before we get there, let us return to the early universe, to the era of galaxies and stars and the slow accumulation of complexity that eventually produced everything we know. The first galaxies formed within the first billion years of the universe's life. They were small by modern standards. Dwarf galaxies containing millions or billions of stars rather than the hundreds of billions found in large modern galaxies like the Milky Way. They were irregular in shape, chaotic, still in the process of assembling themselves from infalling gas and merging with other small proto-galaxies. At the centers of many of these early galaxies, something extraordinary was happening. Supermassive black holes, objects containing millions or billions of times the mass of our Sun, were forming and growing at astonishing rates. Feeding voraciously on the gas flowing into the galactic centers, these black holes were releasing enormous amounts of energy as matter spiraled into them. They were shining as quasars, the most luminous, persistent objects in the universe, outshining entire galaxies of hundreds of billions of stars. How these supermassive black holes formed so quickly, so early in cosmic history, is one of the outstanding unsolved problems in astrophysics. Growing a black hole to billions of solar masses in the first billion years of the universe's history seems to require initial seeds, perhaps stellar mass black holes from population 3 supernovae, and then continuous, nearly uninterrupted accretion at the maximum possible rate. Even so, the math is difficult. Some of the most distant quasars we observe existed when the universe was only a few 100 million years old, and they already contained black holes of several billion solar masses. We do not fully understand how they formed. They seem almost too large, too soon. Over billions of years, small galaxies merged into larger ones. The great cosmic web, driven by dark matter's gravity, channeled gas along filaments toward massive nodes where giant galaxy clusters assembled. Galaxies collided, merged, and reorganized. Spiral structures formed and dissolved. New generations of stars continued to form, live, and die, enriching their host galaxies with heavier elements. And in one spiral galaxy, ordinary, unremarkable, located in a quiet suburb of the cosmic web, something remarkable began about 4.5 billion years ago. A molecular cloud of hydrogen, helium, and small but crucial amounts of heavier elements was collapsing under its own gravity. Inside this cloud, a disk of gas and dust formed around a central concentration of collapsing matter. That concentration grew hotter and denser as it pulled in more and more gas, until at the center, the pressure and temperature reached a threshold, and fusion ignited. A new star was born. Our star, the Sun. It was not alone. As the disk of gas and dust surrounding the young Sun slowly spread and cooled, something extraordinary was happening within it. Tiny grains of dust were colliding and sticking together, forming pebbles, then boulders, then planetesimals, bodies kilometers across. Gravity was accelerating the process, and the planetesimals were colliding and merging into ever larger bodies. Within the inner solar system, where temperatures were too high for volatile compounds like water and methane to condense, the rocky planets were growing. Mercury, Venus, Earth, Mars, each one the product of a billion collisions, a chaotic accretion of rock and metal that took tens of millions of years. Earth was, in its early days, nearly unrecognizable. It was a world of liquid rock and total violence. Large impactors continued to strike the young planet, adding their mass and heat to its growing body. The surface was a magma ocean. There was no crust, no ocean, no atmosphere. Or rather, there was an atmosphere, but it was a toxic mixture of hydrogen and helium and volcanic gases, nothing like what exists today. And then came a collision that changed everything. Approximately 4.5 billion years ago, a body roughly the size of Mars, sometimes called Theia, struck the young Earth in an oblique, glancing blow of almost incomprehensible violence. The impact vaporized the impactor entirely. It melted much of the outer Earth, blasting an enormous quantity of rock and vapor into orbit. That orbiting material, over thousands of years, coalesced into a new body. Our Moon. The Moon is not simply a decoration in our sky. It has played a profound role in Earth's habitability. Its gravitational interaction with Earth stabilizes our planet's axial tilt, preventing the wild swings in axial orientation that would cause catastrophic climate oscillations. It generates tides that may have been crucial to the chemistry of early life. It has, over billions of years, slowed Earth's rotation and made our days longer and our climate more stable. The Moon is not incidental to life on Earth. In some sense, it is part of the story of how life became possible. About 4 billion years ago, as Earth's surface cooled and the first permanent crust formed, water arrived. Some of it was degassed from the cooling mantle, released by volcanic activity. Some arrived aboard comets and asteroids from the outer solar system, icy bodies that had been scattered inward by the gravitational dynamics of the giant planets. Water collected in low-lying regions, forming the first oceans. And in those early oceans, or perhaps in hydrothermal vents on the ocean floor, or in warm, shallow pools, or in some combination of environments, something happened that was, by any measure, the most extraordinary event since the Big Bang. Life began. We do not know exactly when. We do not know exactly where. We do not know exactly how. This remains one of the deepest mysteries in science, perhaps the deepest, because it touches not just on the question of what happened on Earth 4 billion years ago, but on one of the most fundamental questions imaginable. Is life an inevitable consequence of chemistry, given the right conditions? Or is it an almost impossibly improbable accident? Something that may have happened only once in the entire history of the universe. The earliest evidence of life on Earth dates to approximately 3.7 to 3.8 billion years ago. Microscopic fossils, chemical signatures in ancient rocks, suggesting the existence of simple single-celled organisms at almost the earliest time when Earth's surface was hospitable. The speed with which life appeared, within a few 100 million years of Earth's formation, almost as soon as the surface cooled enough to be habitable, suggests that life does not require billions of years to get started. It may arise quickly, under the right conditions. Those first organisms were not complex. They were simple cells without nuclei, prokaryotes, organisms related to the bacteria and archaea that still populate Earth in enormous numbers today. They were chemically sophisticated, certainly. They had already solved the fundamental problems of metabolism, of copying genetic information, of harvesting energy from their environment. But they were small, simple, and invisible to the naked eye. For most of Earth's history, that is all there was. For nearly 2 billion years, from the origin of life to roughly 2 billion years ago, Earth was a world of microbes, a world invisible to the eye, but extraordinary in its chemical complexity. These microbes were not passive. They were transforming the planet. The most consequential transformation came from a group of bacteria called cyanobacteria, organisms that evolved the ability to perform photosynthesis, harvesting energy from sunlight and releasing oxygen as a byproduct. For billions of years, Earth's atmosphere had been largely oxygen-free. Oxygen, the gas we breathe, the gas that makes complex animal life possible, did not exist in significant quantities in the early atmosphere. But cyanobacteria began to change that. Over hundreds of millions of years, as cyanobacteria spread across the ancient oceans, they produced enormous quantities of oxygen. That oxygen reacted with dissolved iron in the seawater, precipitating out as iron oxides and settling to the ocean floor, creating the great banded iron formations we find in ancient rocks today. Eventually, when the dissolved iron was exhausted, oxygen began to accumulate in the atmosphere. The Great Oxidation Event, beginning roughly 2.5 billion years ago, was a catastrophe for most life on Earth. The organisms that had dominated for billions of years were adapted to a world without oxygen. For them, oxygen was poison. They retreated to anaerobic environments, deep sediments, hydrothermal vents, the guts of other organisms, where they persist to this day. But for some organisms, oxygen was an opportunity, and the evolution of aerobic metabolism, the ability to burn organic compounds with oxygen, unlocked enormous amounts of energy. Organisms that could do this were far more energetically capable than their anaerobic cousins. The oxygen-rich world was, for the organisms that could exploit it, a world of abundance. And then, perhaps the most important evolutionary event after the origin of life itself, the emergence of the eukaryotic cell. Eukaryotic cells are larger and more complex than prokaryotic cells. They have a nucleus, a membrane-enclosed compartment containing the cell's genetic material. They have a complex internal architecture of organelles, and crucially, they have mitochondria, the powerhouses of the cell. The origin of mitochondria is one of the most beautiful stories in evolutionary biology. Mitochondria are not descended from the original eukaryotic cell. They are descended from bacteria, ancient proteobacteria that were engulfed by a host cell around 2 billion years ago, and instead of being digested, formed a permanent symbiotic relationship. Over millions of years, the engulfed bacterium lost most of its genes, transferring them to the host cell's nucleus, and became the mitochondria we have today. We carry ancient bacteria inside every cell of our bodies. Every time a cell in your body produces energy, it is using the machinery of a 2 billion-year-old symbiosis. Every breath you take feeds the descendants of bacteria that helped shape the history of life. The eukaryotic cell was a platform for the evolution of complexity. Eukaryotic cells could become large, they could differentiate, they could specialize, and eventually they could cooperate, joining together to form multicellular organisms. For over 1 billion years, multicellular life remained simple. Thin films of cells, colonial organisms, the ancestors of algae and fungi. And then, approximately 540 million years ago, in what geologists call the Cambrian explosion, the history of life changed in a way that still astonishes scientists. In the geological record, the transition from the late Precambrian to the early Cambrian represents one of the most dramatic shifts in the diversity of life in Earth's history. Animal body plans proliferated with extraordinary speed, in geological terms. Creatures with eyes, with limbs, with nervous systems, with hard shells and exoskeletons appeared in the fossil record within a geologically brief window of perhaps 20 to 30 million years. The causes of the Cambrian explosion are debated. Some researchers point to rising oxygen levels that finally crossed a threshold sufficient to support active, motile animals with high energy demands. Others point to changes in ocean chemistry. Others to evolutionary triggers. the development of key genetic innovations like the Hox genes that control body development, or the predator-prey arms race that drove rapid evolutionary innovation. Whatever the cause, the Cambrian explosion launched an era of biological invention that, in terms of sheer novelty, has never been equaled. The basic body plans of virtually all living animal groups were established in the Cambrian, or shortly thereafter. And from that explosion of complexity, life continued its long journey through the ages of the Earth. Fishes colonized the seas. Plants colonized the land, transforming the bare rock of the continents into green, oxygen-rich ecosystems. Insects appeared and diversified. Amphibians ventured onto land. Reptiles evolved and conquered the land entirely. And in the Mesozoic era, beginning roughly 250 million years ago, one group of reptiles underwent an extraordinary radiation: the dinosaurs. For 150 million years, dinosaurs dominated the land. Their diversity was staggering, from the tiny feathered theropods to the enormous titanosaur sauropods that represent the largest land animals in Earth's history. They were not the slow, cold-blooded, dim-witted creatures of early imagination. Many were active, warm-blooded, socially complex. Some developed feathers. Some gave rise to the birds. And 66 million years ago, a piece of rock approximately 10 kilometers across struck the Earth at what is now the Yucatan Peninsula of Mexico, releasing energy equivalent to billions of nuclear weapons in a single instant. The impact was the beginning of the end for the non-avian dinosaurs. The energy of the impact set off global wildfires. The vaporized rock and the soot from those fires blocked sunlight around the world, triggering a sudden and severe drop in temperatures. Photosynthesis collapsed. Food chains collapsed. About 75% of all species on Earth went extinct in the geological instant following the impact. The Cretaceous-Paleogene extinction event is one of the 5 major mass extinctions in Earth's history. Moments when the great arc of biological evolution was interrupted by catastrophe, and life had to begin again, building new ecosystems from the survivors. Those survivors, after the asteroid winter, found themselves in a world of empty ecological niches. And one group in particular, small, warm-blooded, furry creatures that had spent the age of dinosaurs in the shadows, living nocturnally, eating insects and seeds, now found themselves in a transformed world. Mammals. Over the tens of millions of years following the extinction event, mammals diversified with extraordinary speed, filling every ecological role vacated by the dinosaurs. Hooves and horns and trunks and wings and fins emerged as mammals, adapted to every available habitat. And among the many lineages that diversified, one group of small, tree-dwelling, visually oriented creatures with grasping hands and forward-facing eyes began an evolutionary journey that would lead, eventually, to something unprecedented: the primates. Primate evolution is a long story, marked by gradual increases in brain size relative to body mass, by the development of increasingly sophisticated tool use and social behavior, by the emergence of larger and larger-brained apes in the Miocene epoch. And then, in Africa, approximately 6 to 7 million years ago, one lineage split from the ancestors of chimpanzees, the hominins. The hominin lineage was distinguished from the beginning by an unusual commitment to upright walking, bipedalism. It freed the hands for other uses. It changed the energetics of movement. It brought the skull to a different position relative to the spine, allowing for gradual changes in skull shape and brain architecture. Over millions of years, hominin brain sizes increased, generation by generation. Tools became more sophisticated. Social groups became larger and more complex. A control of fire, perhaps as early as 1,000,000 years ago. A capacity for language, perhaps 400,000 years ago, perhaps longer. And finally, in Africa, approximately 300,000 years ago, a hominin whose anatomy was recognizably modern, Homo sapiens, appeared. Our species, us. For most of those 300,000 years, we were, by any cosmic measure, unremarkable. Small bands of nomadic hunters and gatherers, roaming the landscapes of Africa and, eventually, spreading across the globe. Our populations were small. Our impact on the planet was limited by the capabilities of our technology. But we carried something inside us, something that no other species on Earth possessed in quite the same way. We carried the capacity to imagine things that did not exist, and then make them real. We could think not just about what is, but about what could be. We could cooperate with strangers who shared our values and beliefs without knowing them personally. We could accumulate knowledge across generations, building on the discoveries of the dead. Agriculture emerged roughly 10 to 12,000 years ago. Cities, writing, mathematics, science, and in a geological eye blink, in less time than it takes for a single geological stratum to form, a species of primate from Africa had gone from stone tools to microchips, from counting on fingers to calculating the curvature of space-time, from wondering at the stars to sending machines beyond the solar system. The universe had, through an unbroken chain of processes beginning at the first instant, produced something that could look back at itself and ask why. That is not a small thing. You are not separate from the universe looking at it from outside. You are the universe looking at itself from inside. The atoms in your body were forged in the cores of stars that exploded billions of years ago. The iron in your blood was created in a supernova. The calcium in your bones, the oxygen in your lungs, the carbon in every molecule of your DNA. All of it was created in stellar furnaces across billions of years of cosmic history. You are the product of nuclear reactions in the hearts of dead stars. And the information in your mind, the neurons firing in patterns that give rise to thoughts and memories, and the experience of understanding, that information traces back through every ancestor to the first living molecule that could copy itself in the warm waters of the early Earth. And that molecule traces back to the chemistry of the solar nebula, and that chemistry traces back to the nuclear physics of early stars, and that traces back to the Big Bang, and to whatever came before. There is no break in the chain. You are continuous with the beginning of everything. But the universe is not finished with its story. And the rest of the story, the part that has not yet happened, is, in some ways, the most astonishing of all. Because we can calculate it. We can project, using the laws of physics as we understand them, what will happen to the universe in the future. Not just the near future, the next billion years, but the far future, extending trillions and quadrillions of years hence to timescales so vast that the current age of the universe, 13.8 billion years, becomes a mere prologue. And what we find, when we follow the equations to their logical conclusions, is a story of slow, majestic, inevitable decline. The present moment, despite everything, despite every struggle and every tragedy and every uncertainty, is, cosmically speaking, a golden age. The universe is still producing stars. It is still young enough for hydrogen gas to remain abundant in galaxies, fueling the formation of new suns. The cosmic web still has enough energy density for new structures to assemble. Life has arisen, and perhaps arisen elsewhere, across what is, by historical standards, a universe in its prime. But this will not last. The universe has a limited supply of hydrogen. The raw material of stars is being consumed, fused into helium, then into heavier elements, locked up in stellar remnants and cold planets and dead matter. Every star that lives and dies reduces the reservoir of available fuel. In approximately 5 billion years, our own sun will exhaust the hydrogen in its core. The core will contract, and the sun will swell into a red giant, ballooning to perhaps 100 times its current diameter. The inner planets, likely including Earth, will be swallowed or scorched to bare rock. Whatever remains of civilization at that point, if anything does, will have long since had to find another home. The sun, after its red giant phase, will shed its outer layers in a beautiful expanding shell of gas, a planetary nebula, and the core will remain as a white dwarf. A dense, Earth-sized ball of carbon and oxygen, slowly cooling over billions of years from white-hot to yellow to orange to red to black. This is the fate of the majority of stars, to end as white dwarfs. The very largest stars, those with masses more than 8 times our sun's, will undergo a more violent end, exploding as supernovae and leaving behind neutron stars or black holes. But those massive stars are a minority. Astronomers project that the Milky Way will eventually exhaust its capacity for new star formation. Gas is consumed by stars. Some is returned by dying stars, but not all. A fraction is permanently locked into stellar remnants. Each generation of stars leaves behind slightly less raw material for the next. The era of star formation will not end instantly. It will dwindle, gradually, over trillions of years. Smaller and smaller stars will be the last to form. Red dwarfs, tiny and dim, with lifespans of tens to hundreds of billions of years. As the remaining gas in galaxies is slowly consumed or lost, star formation will become rarer and rarer, until the last star forms and ignites, and no new fire joins the darkness. On cosmic timescales, this endpoint is not far. Most models suggest that the bulk of star formation in the universe will be complete within 1 to 2 trillion years, roughly 100 times the current age of the universe. After that, the universe enters what physicists sometimes call the degenerate era. In the degenerate era, the universe will be populated almost exclusively by stellar remnants. White dwarfs will cool, slowly, over hundreds of billions to trillions of years, fading from white to yellow, to orange, to red, to infrared, to nothing, becoming black dwarfs, objects that have never yet been observed, because the universe is not old enough for any white dwarf to have cooled that far. Every white dwarf in the current universe is still hot. Neutron stars will persist, extraordinarily dense objects, composed of neutrons packed as densely as an atomic nucleus, spinning rapidly, radiating away their energy as pulsars, and eventually cooling into silence. And black holes, the collapsed remnants of the most massive stars, and the supermassive black holes at the centers of galaxies, will grow. they will continue to accumulate whatever mass falls into them, growing slowly larger as the degenerate era progresses. But even black holes, the most enduring objects in the known universe, are not eternal. In 1974, Stephen Hawking made one of the most astonishing theoretical predictions in the history of physics. Using a combination of quantum mechanics and general relativity, those two great incompatible theories of modern physics, he showed that black holes are not perfectly black. They radiate at the event horizon of a black hole, the boundary of no return, the surface from which not even light can escape. Quantum effects cause pairs of virtual particles to be created from the vacuum. Normally, virtual particle pairs appear and immediately annihilate. But near the event horizon, one of the pair can fall in while the other escapes. The escaping particle carries energy, real energy, and to conserve energy, the black hole loses mass. This process is called Hawking radiation, and it means that every black hole, given enough time, will eventually evaporate completely. For stellar mass black holes, this process takes an almost incomprehensible amount of time, roughly 10 to the 67th years for a black hole of solar mass to evaporate. For supermassive black holes of billions of solar masses, the timescale extends to 10 to the 97th years or beyond. These numbers require a moment of reflection. The current age of the universe is 13.8 billion years, or roughly 10 to the 10th years. The lifetime of a stellar mass black hole, 10 to the 67th years, is 57 orders of magnitude longer than the current age of the universe, a number so large that even the geological concept of deep time is comically inadequate to express it. But Hawking radiation is not instantaneous. It is extraordinarily slow. For large black holes, the power output is infinitesimal, less than a trillionth of a watt for a black hole of solar mass. And as the black hole evaporates and shrinks, it gets hotter and radiates faster, until the final moments of evaporation produce a burst of high-energy radiation, and the black hole winks out of existence. In the very long-term future of the universe, the last black holes will evaporate. And after they are gone, the universe will enter a new phase, sometimes called the Dark Era. But before we get there is another process that may intervene, a process that would fundamentally alter the structure of matter itself. The proton, the building block of all atomic nuclei, and therefore of all ordinary matter, may not be stable forever. Many extensions of the standard model of particle physics predict that protons will eventually decay. Not spontaneously collapse under internal forces, but truly decay, transforming into lighter particles through processes that violate the conservation of baryon number. The predicted half-life of the proton, in many models, is around 10 to the 34th to 10 to the 36th years. If protons do decay, then even the cold, dark remnants of stars and planets, the black dwarfs and cooled neutron stars, will eventually dissolve. Their constituent nuclei will decay into leptons and photons over timescales of perhaps 10 to the 40 years. If protons do not decay, and current experiments have pushed the lower bound on the proton lifetime to greater than 10 to the 34 years without detecting decay, then the cold stellar remnants will persist for even longer. But they will still, eventually, lose mass through quantum tunneling processes, and even cold matter will not be eternal. After the last proton has decayed, after the last black hole has evaporated, after the last particle of ordinary matter has transformed into lower energy states, what remains? Photons of extremely low energy. Neutrinos, perhaps dark matter particles, if they are stable. Gravitons. A universe at a temperature infinitesimally above absolute zero, in a space that has expanded to such enormous scales that the distance between any two particles is measured in numbers beyond any human language. This is the end point of the universe, at least as our current physics describes it. The maximum entropy state, the heat death. Thermodynamics tells us that entropy, the measure of disorder, of the spreading of energy, always increases in a closed system. The Big Bang was a state of low entropy, not because it was disordered, but because the energy was concentrated in a way that could do vast amounts of work. As the universe evolved, entropy increased. Stars converted concentrated gravitational potential energy into dispersed radiation. Life and complexity were temporary, local decreases in entropy, sustained by the flow of energy from hot stars to cold space. But the universe as a whole grew ever more disordered. The heat death is the final state of maximum entropy, a state in which energy is so evenly distributed throughout such an enormous volume that no gradients remain, no hot spots and cold spots, no differences in density or temperature that could drive any physical process. A state of perfect thermodynamic equilibrium. Nothing happens in the heat death. Nothing can happen, because there is no free energy remaining to drive any process. The universe simply exists, enormous, cold, dark, silent, and changeless. Not dead exactly, because there is nothing alive to contrast it with. Not even cold in any meaningful human sense, because there are no temperatures warm enough to give that word meaning by contrast. Just the universe, in its final state, extended across distances so vast that the observable universe we live in today would be an infinitesimal speck compared to the full extent of what remains. And it will stay that way, perhaps forever. This is the future, at least as current physics predicts it. But there is something important to say here, something that changes the character of this bleak conclusion. We do not know that dark energy is constant. The cosmological constant, the form of dark energy described by Einstein's equations, would drive accelerating expansion indefinitely, leading to the heat death on the timescale described. But dark energy might not be a constant. It might be a field, what physicists call quintessence, that evolves over time. If dark energy grows stronger with time, the acceleration of expansion could itself accelerate. Galaxies would be torn apart, then solar systems, then planets, then atoms themselves would be torn apart as the expansion of space became strong enough to overcome every binding force in nature. This scenario is called the Big Rip. If dark energy decays or reverses, the expansion might eventually slow and reverse, leading to a contraction of the universe back to a singularity, a big crunch, potentially followed by another Big Bang in a cyclic cosmology. Some cosmologists have proposed that quantum fluctuations in the vacuum might, on timescales beyond the heat death, occasionally produce a spontaneous decrease in entropy, a fluctuation large enough to create, by chance, a new pocket of low-entropy physics. In an infinite sea of maximum entropy, random fluctuations might occasionally generate something, perhaps even a new universe. And some cosmologists take seriously the possibility that the vacuum of our universe is not truly stable, that it occupies a false vacuum state that is only metastably stable, and that a quantum fluctuation somewhere in the universe might, at some future time, trigger a decay to a lower energy true vacuum state. Such a vacuum decay would propagate outward at the speed of light, transforming the physics of everything it touched, effectively ending the universe as we know it without warning and without any possibility of survival. We do not know if any of these alternatives are true. We do not know the ultimate fate of the universe with certainty, but in every scenario, the conclusion is the same in its broadest strokes. The universe evolves from a state of low entropy to a state of high entropy. The era of structure, of galaxies, stars, planets, life, is not permanent. It is a phase, a complex and beautiful and improbable phase in the long history of a universe that began in a moment of extraordinary order and is moving inexorably toward disorder. And yet, here we are, inside the beautiful phase. Here, in this window of perhaps 1 trillion years, this tiny, precious interval in cosmic history when stars can shine and chemistry can occur and complexity can arise, we exist. Consider what it means that the universe has a history at all. The universe is not static. It is not eternal and unchanging. It had a beginning, an absolute beginning, as far as we can determine, 13.8 billion years ago. And it will have an end, in the broad sense, even if the end is a long time coming. In between the beginning and the end, the universe has evolved through an extraordinary sequence of phases, each one building on the last, each one creating the conditions for the next. From the quark-gluon plasma to the first atoms, from the dark ages to the first stars, from the first stars to the first galaxies, from the first galaxies to the complex, chemically rich universe we inhabit, from primordial chemistry to replicating molecules to eukaryotic cells, to animals, to minds. At each step, new structures emerged that were not predictable from the previous step. Atoms are not predictable from quarks alone. Life is not predictable from chemistry alone. Mind is not predictable from neuroscience alone. Each level of organization has properties, what philosophers call emergent properties, that arise from the interactions of the level below, but cannot be fully reduced to it. This emergence of novelty at each level of cosmic and biological organization is one of the deepest and most fascinating properties of the universe. It suggests that the universe is, in some sense, genuinely creative, capable of producing things that were not implicit in its initial conditions in any simple way. And what is the most complex, most surprising emergent property of this 13.8 billion year creative process? The capacity to ask about it. Consciousness, whatever it is, however it arises from the physical substrate of the brain, is the universe's way of knowing itself. Without minds, all of this history would have happened, but there would be no one to know it happened. There would be no story. There would be events, but no narrative. The fact that the universe has produced beings capable of understanding it, capable of tracing the history of light from the CMB, of calculating the half-life of a proton, of projecting the evaporation of the last black hole, is one of the most remarkable things about it. It is not guaranteed that physics permits consciousness to arise. It is not guaranteed that consciousness arises even where physics permits it. It appears to have happened here, and perhaps, if the universe is large enough and old enough, elsewhere as well. And so the universe has not merely evolved through states of matter and energy. It has evolved into a state that includes understanding. It has evolved into a state where the story can be told. This changes the meaning of everything that came before. The deaths of ancient stars, billions of years before the sun was born, were not merely events in the history of matter. They were the creation of the raw materials for us. The Great Oxidation Event was not merely an ecological catastrophe. It was a necessary step toward the chemistry of complex life. The Chicxulub impact was not merely a mass extinction. It was the event that cleared the stage for mammals, and ultimately for minds. Not by design, not by intention, not guided by any force that wanted a particular outcome, but connected, causally, inevitably, completely connected. Everything that has ever happened in the universe is part of the same unbroken chain that led to this moment, to you, to this act of understanding. There is no escape from the chain. You cannot remove a single event in the 14-billion-year history of the universe without removing everything that followed from it, up to and including this moment. That is a kind of meaning that does not require a designer to be profound. And yet, there are questions that remain. Questions that may be unanswerable given the laws of physics as we currently understand them. What is dark matter? We know it exists from its gravitational effects. We know what it is not. Ordinary matter, neutrinos, black holes. But we do not know what it is. The particle, or particles, or perhaps field, that constitutes the 27% of the universe's energy content that is dark remains undetected in our laboratories. What is dark energy? We know it drives the acceleration of the universe's expansion. We know it constitutes 68% of the universe's energy content. We have measured its density with increasing precision, but we do not know what it is at a fundamental level. The theoretical prediction for the energy density of the vacuum from quantum field theory disagrees with the observed value of dark energy by 120 orders of magnitude. 1 followed by 120 zeros. This is, by a very large margin, the worst prediction in all of physics. Something is profoundly wrong with our understanding. What happened before the Big Bang? Or is that question even meaningful? Our current physics tells us that time began at the Big Bang, that there is no before. But that cannot be the full answer, because the Big Bang itself requires an explanation. Something, inflation, a bounce from a previous contracting universe, a quantum fluctuation in apparent space-time, preceded it in some sense. We do not know what. Why are the constants of nature the values they are? The fine structure constant, the ratio of the proton mass to the electron mass, the gravitational coupling constant. These dimensionless numbers appear to be tuned with extraordinary precision for the existence of complex structures. If they were even slightly different, atoms could not form, or stars could not fuse elements, or the universe would collapse or fly apart before galaxies could assemble. Some physicists find this troubling. Others take it as evidence for the anthropic principle, the idea that we observe a universe hospitable to complexity, because we could not exist to ask the question in any other kind of universe. Others take it as evidence for the multiverse, that there are many universes with many different values of the constants, and we find ourselves in one that permits our existence. Others suspect there is a deeper reason, a deeper theory that will explain why the constants take the values they do. We do not know. Is there life elsewhere in the universe? The question that haunts us, that has haunted us since we first understood the scale of the cosmos. The universe contains approximately 2 trillion galaxies, each containing hundreds of billions of stars. Many of those stars have planets. We now know, from the Kepler mission and its successors, that planets are common. Rocky, potentially habitable planets exist in enormous numbers throughout the galaxy. And yet, we have found no signal of life beyond Earth. The Fermi paradox, the question of why, given the apparent conditions for life in the universe, we have found no evidence of any other civilization, remains one of the most troubling and unresolved questions in science and philosophy. The silence of the cosmos may mean that life is extraordinarily rare. It may mean that complex life arises easily, but intelligent life is vanishingly improbable. It may mean that civilizations inevitably destroy themselves before they become detectable. It may mean that we are simply not listening in the right way. It may mean something entirely different, something we have not yet thought of. The answer, if one exists, would be the most important discovery in human history. These are not peripheral questions. They go to the heart of what the universe is and what we are within it. We live at an extraordinary moment in the history of knowledge. We know, with precision and confidence, the age of the universe, its geometry, its composition, the history of its first 3 minutes. We can model the formation of galaxies from quantum fluctuations in the first instant. We can trace the nuclear reactions in dying stars that created the atoms in our bodies. We have extended our knowledge of cosmic history across more than 13 billion years, and yet 95% of the universe remains, in some fundamental sense, unknown. The era of major discovery in cosmology is not over. It has barely begun. The James Webb Space Telescope, launched in 2021, is revealing the first galaxies of the universe with a clarity that was impossible before. It is observing the light of stars from within the first few 100 million years of cosmic history, during the epoch of ionization, when the first stars flooded space with enough ultraviolet radiation to ionize the neutral hydrogen of the cosmic dark ages. Every image it returns is a step deeper into the universe's past. Future gravitational wave detectors may reveal new classes of cosmic events and new tests of general relativity in the strong field regime. Future dark matter detectors may, at last, detect the particles that constitute the invisible scaffold of the universe. Future particle colliders may discover new physics beyond the standard model, revealing new forces and new particles that point toward a deeper description of reality. And future generations of cosmologists may ask questions that we have not yet thought to ask, using tools that have not yet been built, discovering things that are currently beyond our imagination. That is the nature of discovery, not a march toward a known destination, but an exploration into genuine unknown, where the territory itself defines the path. Let us step back one final time and look at the whole. 13.8 billion years ago, from conditions that we cannot fully describe, the universe began. In its first moments, it passed through states of extraordinary density and temperature, creating the elementary particles that would eventually form all matter. In its first few minutes, the fundamental chemistry of the cosmos was established. Mostly hydrogen, some helium, traces of lighter elements. Over the next 380,000 years, the universe cooled from a glowing plasma to a transparent gas, releasing the light we now call the cosmic microwave background. In the cosmic dark ages that followed, the first structures assembled themselves from the gradual accumulation of slightly denser regions. The first stars ignited, burning hot and brief, seeding space with the heavy elements forged in their cores and scattered in their depths. Galaxies formed and merged and grew. Supermassive black holes assembled at galactic centers and blazed as quasars. The universe built complexity from simplicity, structure from uniformity, diversity from a nearly featureless beginning. In one galaxy, in one arm of one galaxy, around one ordinary star, a small rocky planet formed. That planet gathered water, developed an atmosphere, and within a few 100 million years of its surface cooling, the first living cells appeared in its oceans. For billions of years, life was simple and microbial, transforming the planet's chemistry and atmosphere. And then, with the evolution of complex cells and multicellular organisms, the pace of biological evolution accelerated. Animals arose, the ocean filled with complex life. Creatures conquered the land. Forests appeared. Dinosaurs ruled the land for 150 million years, and when an asteroid ended their era, mammals inherited a transformed world. From those small, warm-blooded survivors came an extraordinary radiation of life forms, culminating in a species of upright walking, large-brained primates that developed language, culture, and science. That species, you, us, Homo sapiens, has in the last few centuries developed the capacity to understand, with genuine precision, the history of the universe that produced it, to read the light of the oldest photons, to detect the gravitational ripples of colliding black holes a billion light-years away, to reconstruct the nuclear processes in the cores of ancient stars from the composition of modern gas clouds, to project the future of the cosmos from the present state of its expansion. We are, to the best of our knowledge, the universe's first and perhaps only act of self-awareness. And what do we see when the universe looks back at itself? We see a cosmos of terrifying scale and astonishing beauty. We see a history of almost incomprehensible duration, within which our entire civilization is a flash too brief to register on the cosmic timescale. We see a future of similar duration, a long, slow decline from the brief brilliance of the stellar era to the cold, dark, silent endpoint of maximum entropy. We see 95% of the universe that we do not understand. We see the deep waters of mystery that surround the small island of our knowledge. We see questions that may be answerable and questions that may not be, questions about the nature of dark matter and dark energy, about what existed before the Big Bang, about whether we are alone. And we see, if we are honest with ourselves, that the universe did not produce us because it needed us, or wanted us, or intended us. We are the product of physics and chemistry and biology operating over an immense span of time, according to laws that are, as far as we can tell, indifferent to our existence. We are not the purpose of the universe. We are a consequence of it. And yet, we are here. We exist in this brief interval between the long darkness of the past and the long darkness of the future. We have the capacity to understand, to wonder, to find beauty in the equations and in the stars and in the story. We have the capacity to feel the weight of the cosmos and not be crushed by it. That capacity may be, in the end, the most astonishing thing in the universe. Because for all its size, for all its duration, for all its complexity, the universe itself does not know that it exists. It does not experience the aurora of a winter sky. It does not feel the force of a mathematical proof. It does not find the death of ancient stars beautiful, or the birth of a new star moving. We do. And that changes what it means to be a small creature in a large universe. It does not make us large. It does not make the universe small. It does not close the gap between the scale of a human life and the scale of cosmic history. But it does mean that we carry something the universe does not have without us. We carry the meaning that we make, the stories we tell about stars, the questions we ask about beginnings and ends, the wonder we feel when we contemplate the immensity of what exists and the improbability of our place within it. The universe began in fire and will end in the cold silence of maximum entropy. In between, for a brief and beautiful moment, measured in trillions of years, there is light. There are stars and planets and oceans and creatures that look up at the night sky and wonder. We are in that moment right now. We are part of the light. And the light, however brief, is worth everything. There is one more thing worth saying, something that lives not in the realm of certainty, but in the borderlands where science meets philosophy, where what we know begins to shade into what we can barely imagine. The question of what the universe is for, if it is for anything, may not have an answer accessible to us. The equations do not tell us. The observations do not tell us. The history of 13.8 billion years does not, in itself, offer a purpose. But there is a perspective from which the story we have just told looks different. Not from a religious perspective necessarily, nor from a purely materialist one. From the perspective of complexity itself. The universe began in a state of extraordinary simplicity. A plasma of elementary particles, barely differentiated, nearly uniform. And over time, it moved relentlessly toward complexity. Not because complexity was programmed in, not because some force was steering it there, but because the laws of physics, applied consistently over vast timescales in a low-entropy universe, drive the emergence of structure. Gravity clumps matter into stars. Stars fuse simple nuclei into complex ones. Supernovae scatter those nuclei into space. Chemistry assembles complex molecules. Evolution assembles complex organisms. Minds assemble complex ideas. The universe appears to have a bias toward complexity. Not in the thermodynamic sense. Thermodynamics drives toward disorder. But locally, in the presence of energy flows from hot sources to cold sinks, complexity can accumulate and persist. Life is the most extreme example of this local complexity. Systems so organized, so information-rich, so far from thermodynamic equilibrium that they represent something qualitatively different from anything that simple physics produces. And minds are the most extreme version of life. We are the universe's most complex local departure from equilibrium. We are the furthest thing that the Big Bang has yet produced from the simplicity it started with. Whether that means anything beyond itself, whether complexity is heading somewhere, whether there is a direction to this story, is not a question science can answer. But it is the right question to ask, and asking it is part of what makes us what we are. The cosmos does not need us to exist, but we, in some sense that defies easy articulation, need the cosmos to exist. It is the ground of everything we are, and everything we know, and everything we love. We are made of it. We are expressions of it. And when we look up at the night sky, at the stars we now know are thermonuclear furnaces, at the galaxies we now know are islands of hundreds of billions of suns, at the faint smear of light across the sky we now know is the edge on view of our own 100,000 light-year-wide galaxy. We are not looking at something foreign to ourselves. We are looking at ourselves from a distance of billions of years and billions of light-years, reflected in the oldest light in the universe. The history of everything, from the first quantum fluctuation before inflation to the last photon before the heat death, is one continuous story. And we are, at this moment, writing one of its chapters, small and brief and improbable, but undeniably, unmistakably here. That is not a small thing. In a universe of 10 to the 80 protons, of 2 trillion galaxies, of a lifespan extending to 10 to the 100 years and beyond, in all of that vastness and duration, awareness arose. Here, now, in you. That is the universe, at the peak of its creative powers, looking back at the fire that made it, and understanding, for the first time, what it has done. The story is not over, and the most important chapters may still be ahead.